And how's everyone doing today? Has this been a good VCF or what? Excellent. They do great work here. And again, every compliment on earth to the whole team, the volunteers, Jeff Brace and company, who I guess was the leader of the band with all this. They did super work. And if this was a restaurant, I'd say tip early and tip often. But no, they've just done a fabulous thing. Anyway, so I'm Frank O'Brien. I've been here at InfoAid for about 20 years. The thing that brought me in, and it's too long of a story to tell, but is this little toy here. This is a prototype, not an actual flight model, a prototype of the Apollo guidance computer. The real one, which Marc and his compatriots put together, is just friggin' big. Weighs what, 70 pounds, something like that?
Yeah, 70 pounds.
Yeah, you're not going to get that on an airline quickly and easily and all the rest. So this is
you did.
I flew it all for the 50th anniversary of Apollo 11. It flew in the seat next to me as a seat. I bought the seat,
okay, that worked.
It flew all over the Northeast.
Yeah, you see, he's a superior form of life.
It's a miniature aerospace computer.
Yeah, yeah. Anyway, so we have a whole bunch of things to talk about. Marc is going to be giving a little presentation on the restoration work, which I think is just amazing and fascinating. If you haven't gone through all the YouTube videos, this is a nice summary of it. But the one thing, I have just a couple quick things before you start. You have, and again, you have a picture of the team of 4. One gentleman couldn't be here, sadly. How'd you assemble your team?
We used to work, we met at the Computer History Museum working on restorations of the IBM 1401, large. It's a mainframe. It's not large by IBM standards, but it's large by
it's large
standards.
For its day.
And then we broke off and did our own restorations. In particular, we restored an Alto and all kind of difficult things. So that's how, I'll tell the story of how we got to it. But it's through Mike, who unfortunately can't be there, but has a, he's the one that went after us to help him out.
Yeah, he knew Ken. So
yeah, it's through Ken's Swiss blog. And all right. Yeah. Should I go right in?
Just real quick. Let me just look through my notes here and all the rest. You have lots of... One of the incredible things is that, of course, they're the proud owners of a real, honest-to-God Apollo guidance computer. If I'm not mistaken, it was designated for LEM 9.
8.
Oh, I was only off by one.
Not LTA 8.
Oh, okay.
LEM test Article 8.
Got it. Anyway, I hope in your talk you're going to just give a little background on how the heck you acquired that.
Okay.
Well, what do you say? Because you guys aren't here to listen to me. You're here to listen to them, and of course watch the slides. Is that bright enough? Do we need to drop the lights a bit? You're good? Perfect. Take it away.
Okay, so first thing off, it's too big for one person to do it. So it was a group effort, us 3, and then Mike Stewart, who we'll see has as a main important place in the story, if not the main place, is our lead restorer. And also other people that got the documentation. There's plenty of people involved helping us out. Block 2 Apollo guidance computer, that's what it looks like, 70 pounds in the case, and then there's the interface, which is the infamous disk key. You just interact in real time with a simplified keyboard and a very, very beautiful electroluminescent display. And I mean, you should show it. This is a real one. I don't know why you say it's not the real thing. It is one of the real things. Maybe you can hold it. This is half of it. This is the bottom half.
This would be considered the CPU. The second tray, as they're referred to, contains the memory and timing and all that stuff. We don't have that. So again, if the option was to get either the CPU or the rest of it, I'm glad we ended up with this.
Okay. So where does it sit? There are 2 of them, identical machine running different software. One's the command module, and it's in the lower bay. That's the orange part of this thing. And you see there's 2 disk keys. There's one that's the nav disk key that's used to align the telescope and the gyroscopic platform. And there's the other main disk key that's on the command panel. And there's one on the LEM, and on the LEM it sits at the back of the LEM. And actually in the Lego LEM, they have a little AGC brick. I was like stoked about that. So what did the AGC do? And I'm not making that up. That is from Dan Lickley, who programmed the re-entry that was interviewed at the Computer History Museum in 2019. He had same here, where roundtable as a moderator. First question: what did the AGC do in the Apollo mission? And then he rolled his eye back, thought for 10 seconds, says, "It did everything." And it really does, right? So it's not just a computer; it's a computer with a gyroscopic platform hooked up to every single bit of the spacecraft. So it orients the spacecraft, it controls all the burns, it does the guidance calculations, it's also the digital autopilot and fly-by-wire. So even when Armstrong takes the LEM manually, he doesn't. This is always a computer between you and the engines. That's how the LEM is balanced, for example. Of course, it guides the LEM landing, which was, the LEM landing was not considered to be flyable by a human. It's a suicide burn, right? The SpaceX still does it that way. And that you can't do a suicide burn by hand. You have to go and hit it exactly right. And of course, it does the re-entry, which was not also not flyable by hand. So the Russians had totally ballistic, and they would land plus or minus a few hundred miles. The re-entry in the command module is guided, and they got it to a few miles. So that's because of the AGC. Very pioneering system. It's the first time you have a digital computer piloting an aircraft. There were some analog that were made before. And of course, you start with not an aircraft, but a spacecraft. It's very small, quote unquote, 70 pounds, 50 watts at the time where computers filled entire rooms. The first computer to use ICs, and that was the decision of Eldon Hall, the designer. We'll talk about him in a minute. Very controversial decision, but it really made the whole difference. Interactive computer, real time, you talk to it, so you don't have CRTs, but you have a disk key, that's the equivalent. Groundbreaking in the software also, it's a multitasking OS that's checkpointed and recovers from a crash in a second or so.
So all of those alarms you heard during the Apollo 11 landing, 12:02, the computer was restarting, and it would do that within a second and continue guiding the thing down. So it's just amazing.
Now, a key thing about this restart, now when we say restart, the first thing you think of, oh, we're rebooting. You're landing on the moon. The last thing you want is to wipe memory and start all over when it has no idea, then it'll have no idea where it is, where it's going, or why it's there. So we had several different types of restart recoveries. In this case, in the Apollo 11 case, the option was simply, I have a certain amount of problems. The specific problem was out of process slots. I'm just going to throw away all my work, and we're just going to restart from that checkpoint. And it worked like a champ.
Yeah, it picks up from where it was left at. With the little memory that they had is just remarkable. Still waiting for that feature to appear in Windows. Designed by MIT, and it's you can see that there's some academic aspect to it. It's more imaginative than the regular computer at the time, but built by Raytheon, which had built missiles and just very high quality build. Eldon Hall, principal engineer, MIT Instrumentation Lab, which was now called as Draper Lab, still exists. Draper being the inventor of a gyro navigation.
They got the only non-competitive contract for Apollo, for NASA. They said, you've got it, there's nobody else who can bid.
And IBM.
It was also the first contract of Apollo.
Yes, yes. So how do we got our hands on it? Well, through a bizarre twist of fate. So it belonged to this man, Jimmy Locke, who is like us, a tinker, a hacker, and is not a very rich man. That's an understatement. And he lives in Houston, and actually he had worked for a very short time on the Apollo program as a test person, as many people were hired at that time. And then a few years later, 74, I think, he does like we do. He goes to the scrappers, right, and to get cheap parts. And he recognizes Apollo hardware. And he asks the scrappers what it is. They confirm, yeah, this is Apollo. And the scrappers lets him know that he hates it. He doesn't like it. It has all kind of non-recyclable metal. There's this weird stuff. He wants to get rid of it. Say, oh, can I buy some? I say, sure. And he took 2 tons of it. And Apollo scrap, right? Your government, when you have to scrap your stuff, and it's the 70s, right? This old stuff, we are going to do the shuttle, we're going to Mars, blah, blah, blah. So you can't get rid of it. You cannot give it to your favorite engineer. You have to auction it off. And the only person that wanted one was a scrapper. And then this guy bought it, and he didn't even know there was an AGC in it. And so that's when Mike enters the picture. He's a space engineer, writes software, fascinated by as all of the better engineers, they know only their stuff, but they know the history of their stuff. I think that's a mark of the top-tier engineer. And he works with other very gifted people on a simulation. It's called Orbiter, and they have a plugin. Orbiter is a general-purpose simulation program, but they have a plugin to reproduce the Apollo flight to very exact detail. It's extremely well made. And to reproduce it perfectly, they decide they will have an emulation of the AGC running the actual software. And Mike has spent a lot of time, they have spent, at least collectively, a lot of time recovering all the document, the source code, recompiling it, blah, blah, blah. And they make an emulation based on the spec of the computer, emulating each one of the instructions. And they end up always running into trouble. It's corner cases where it never works. And Mike participates in that program and says, guys, we're never going to find out from the NASA documentation. The only way we're going to find out if we build some hardware that's gate exact. Then he goes on a long hunt to get the schematics. He will eventually get them partially from Eldon Hall, the designer, and then Don Iles, the guy that programmed the P-63, the descent program, the landing. And he starts to build a replica in FPGA with all the right gates at the right place. And while he's doing that, he realizes that the schematics are not enough. He needs to know how this thing is wired in the backplane. And so he needs to find somebody that has either the schematic of the backplane, doesn't find one, or somebody that has a real one and is willing to open it up. Turns out Jimmy, who wants to sell this computer, is going to exhibit at Space Fest in 2018, and he calls Jimmy. He says, well, would you mind if I opened it up and beeped it out? And that computer had been opened up before, actually, by Eldon Hall himself. So Jimmy said, well, sure, come on, beep it out. It will give him more coverage. And Jimmy told us that if he wouldn't have pried Mike from the computer, in the evening, he would have slept in it. So he beeped it out and completed his model and got it to work. But while he was doing that, Jimmy asked him, what about powering it up? Could we power it up? And I was a little taken aback. And I said, well, why not? I need help from restorers. And we're well known. He reaches out to us. And we drop all the stuff we're doing. And so the goal here would be to restore it, but to make it work before the 50th anniversary
Of Apollo 11.
Of Apollo 11 landing. So we don't have much time. So we agree to help him out. And Jimmy can't be separated from his computer. So it has to be in Houston, but Jimmy is not well off. He's a little bit ashamed to have it in our house. So is it you or is it Mike that arranges a room?
I think Mike arranged it, right?
Or arranges a room in a hotel And we spent 2 weeks in the hotel with that computer without letting the
room service in. Nobody could come in. We had signs, stay out. They probably thought we were, making drugs or something.
So yeah, I was expecting the FBI to show up. So we're faced for the I'm faced for the first time with that computer. I never seen one, and that's how I felt, right? We have the holy computer in front of us, and my goodness, is it beautiful hardware. So 2 trays. Tray A, that's the one on the right of that picture, that has all the logic modules. And tray B, which is mostly memory. You can see the stick of core memory in the middle, that's the black one. And then the ROM, which is core rope, goes into the slot at the back. It's not populated in that picture. Can you just pick up yours and show it to the audience, because it's
just hold it up.
It's just remarkable hardware.
That's only 35 pounds. It's only half.
Very, very beautiful. So it's very modular, and that's the modules have their roots back to the Polaris missile. So MIT did the Polaris missile, which is an ICBM launch submarines, and had guidance, right? So if you ever see a Polaris thing, it has the similar module. So they just keep working on that. Spectacular hardware. Another beauty view of the tray A modules, and the wires at the top are from the power supplies, and then you notice that you can actually see the wires in it. More on that in a minute. And then this wire wrap backplane, so that's also something that came from the Polaris. They found wire wrap to be much more reliable than PCBs and soldering at the time. And actually, it's extremely reliable.
It is wonderful. Yeah.
We work on the 1401, and we have very rarely a problem with the backplane.
And it's all machine wrapped. There was like these Gardner Denver machines that would take punch cards and do all the wrapping for you. So it was you're fairly efficient for the time and accurate.
Automatic construction, 3-level wire wrap. Yeah. Gardner Denver.
One of the things that when Eldon did his disassembly and all the rest, what we mentioned, again, this is 20 years ago, he was amazed because you guys ended up being very lucky. The wire wrap area was supposed to be embedded in resin. Yeah, that would have really complicated your day.
Yeah, so that's it's coming up. You're ahead of me here.
I'm sorry, we were just...
So it's Ray 14, so Ray stands for Raytheon, of the series 2003-100, which is the engineering test series, the 15 that they'll go for qualification and put through hell, which will pass hell. And this one was actually used in the certification of the LEM LTA-8 in Houston. So it didn't fly in a real mission, but it flew inside of a vacuum chamber with astronauts in the freaking thing. And as you just mentioned, the beauty of it is it's not potted. So normally this thing would be filled with resin and you can't have access to the circuit. This one, since it was not flight qualified, it was still a pre-production, we have access to the components, which is hallelujah, right? If something bad happens, we can get in it. So you can see all the ICs in there. It's on 2 sides, so there's 120 ICs per module. And they are not soldered, they are welded, which is also much, much stronger than soldering. And they're sitting on a 7-layer PCB. And your eyes are not deceiving you, those are surface-mounted components.
Yeah, in the 1960s.
So
multi-layer circuit boards really came into vogue when? About 5-10 years later?
This is stuff that you wouldn't get in the general public until 1980. Right?
Yeah, surface mount didn't catch on with general electronics until the 80s.
Who innovated this? Is this straight for labs?
Yeah, it's the Draper Labs, the MIT instrumentation.
Well, yes, with Raytheon too. So it's both of them. But I had the guy. We talked to the guy that developed the 7-layer PCB thing, and then was trying to sell it after. I said, guys, don't use this 2-layer horrible thing that's unreliable. Use this. But of course, the price point was impossible, right? But the people that he presented to say this is new technology, and it was in the mid-70s. No, it's 10 years old, right?
Yeah, blind vias, all sorts of things you just would never see at this time.
It's unbelievable. And so we have the digital ICs, dual 3-input NOR gates. So they knew they would have to pull or jumpstart the IC industry. So they decided to do just one type of IC. The whole thing is just 3-input NOR gates. And there's a little bit over 5,000. I heard 5,200 or 5,700 gates in the computer. Yeah, on the question, we're going to be stingy. We want them at the end if possible.
Just hang on. We will get to it.
And I thought this was the only IC. That's always I heard. No, there's another one, also way less of them. There is also the first analog IC, and these are used as the sense amplifier for the core memory. So there are 16 of them. So here's a row of 8. They are the thing. They are not the red thing. The red thing is a little transformer. They are the little inverted TO can at the bottom, and that's the first comparator IC. So I said that normally modules would be potted, and a potted module looks like this. You see the black resin is incredibly tough. And it turns out we had 2 modules that were potted in this computer, and strangely did not belong to the original. So this is the current, they are both associated with memory. This is the current switch B11. And this is it's written on it upside down, but no, you have done business before, so you know how to read upside down. It's erasable memory module B12. That's the core memory. And
that's 4K, all in that little space.
Yes, 4K, extremely dense.
2K words.
2K words, or there's 16 bits. Right. Yeah, 4K, but 4K bytes. So really not much to go to the moon. And what are the chances that our main faults will be in the potted modules, right?
Hint.
Hint, hint, exactly. So since we have Mike in the team, we are armed to the teeth. So we were presented the restoration on the silver platter. He has the whole schematics, which had verified it works. He has a replica which is made on an FPGA, cycle exact, and you even see some little glitches. I know you cannot see my mouse, but there's a little glitch over there. We would actually see that in a real one. So it's precise to the nth degree. And then we know how do we approach this, and that's where we start testing it. We just don't power it on, right? So the first thing that we did, and Carl, you were the first one to touch this, you tested the modules. So
we start going through the schematics, and you're trying to check 60 gates. Some of them are sort of inside, not on the outside pins. You have to figure out what's a test method that will verify that every gate works with every combination of the 3 things. So there's a lot of noodling that Mike and I had to do to figure out how to inject test signals to check out every gate. And we were going fine. We found one module where one gate wasn't working right. And we remembered that one of the problems they had early on with the integrated circuits was that bits of metal would get inside the package and short things. And so we just tapped it sideways, put it down, and it worked. Fixed.
And that's the only gate
that's the only gate that failed.
Had a problem. So as I remember well, first you were very cautious because I came a little bit later. I came a week later than those guys, and you tested it gate by gate, making sure they could test gate by gate. And then at some point,
you get through like 15 modules, not been one failure. You say, you know.
And then we tested module by module, but we tested all the modules, right? So a cautious approach, and of course, modules check good, to our surprise, except one that you have to shake. And then power supplies. So of course, power supplies, we want to check the caps. And it turns out, so the power supplies, the analog modules, they are cordwood. So it's components in a block of metal that are drilled, and you shove them through the block that does the cooling, and then you wire
On
the
both
rest.
sides.
Welded nickel wire, also very, very strong. And it turns all the capacitors are accessible, hallelujah, and they are not your average electrolytics. They are tantalum. Every tantalum had been X-rayed to make sure it was free of defect. Not one problem with the electrolytics. So we go on. We still have some other problems. So the first bad news, the core memory module 12 is core rope, right? Core rope is
Core memory.
core memory. So it's little cores with wires going through them. So you can test them by continuity if the wires go through them, and one wire doesn't go through. So oops, we know we have a problem.
A bad problem, a very bad problem.
Right, inhibit 15, which means, that's going to be a little bit complicated to explain, but
But basically, it would rewrite everything to ones in that bit, no matter what you intended.
yeah, actually that's the simplest way to say it. So core memory is destructive. We'll be able to read it once, but after you read it once, you need to rewrite it, and the inhibit is what you use to rewrite it correctly, and we would have lost of all of our bit 15, the entire memory after reading the first one. So that's a bummer. And then this unit didn't come with its ropes, which are rope memory, which is ROM, which is another type of memory based on core, which is called core rope memory, a whole complicated video on that one. But it's not what you want to use when you use a computer for development. So after LTA8, obviously this one was used for development. So what do you use? You use a core rope emulator that will take its memory from a main computer and will emulate a ROM. And so that's what we have. We have these boxes. Ken is holding one.
So how many schematics did we have of that, Ken?
0. We didn't even have a mention of this box in any of the documents.
Any Apollo documentation?
So was it written on it that it was core rope emulation, or we just thought it was? It had to be, right?
Ken figured it out.
So Ken is a master of reverse engineering in the team. He, actually we elect him as the king of the core rope emulator. And there's absolutely nothing on this one. So you do as you usually, you start reverse engineering it.
So
How do you do that?
So yeah, it was basically brute force to reverse engineer this. It was basically prototyping boards that were wire wrapped with hundreds and hundreds of identical blue wires. So I just had to beep out all the wires, make a connection, make the schematics. There was also a lot of analog components because it was simulating the analog signals that you would get from the core rope memory, these little pulses. So I had to figure out how the pulse transformers were wired up. And once I had the schematics, then I had to figure out, what were they actually trying to do here, and put yourself in the mind of the creators and figure out what signals are they taking in, what are they trying to get out. Then once I had it figured out, I built a BeagleBone board that I could feed in the data we wanted, so we could use these, put them into the computer, and then feed in the data we wanted for it to execute a program, and then we'd be able to execute whatever we wanted. But it was a big pain.
Yeah, this was a big effort. So yes, you also had to figure out what computer it was attached to, what was it supposed to give it. We'll go back on that one. So I'm the test guy, so I brought my logic analyzer, and so power supplies, we check them out separately. They come up right on the dot. The 4 volts come at 4.0 something
Yes,
volts.
it's like almost all zero.
And the 14 volts come at 13.99 or something like that. It's just that's not normal for 15 years old electronics, right?
And probably the 0.001 difference was the multimeter and not the power supplies.
We should have calibrated it from the power supply. So we're going in power supply. And then Mike tells us that we should be able to power this thing up with no RAM and no ROM, and we should see it trying to start. So I hook up my logic analyzer, and the thing has a 12 sub-steps. So I am hooked up to every one of the 12 sub-steps. We turn it on. We release the init, and we see the 12 sub-step. It's trying to boot. It's trying to work right off the bat, which we totally did not expect. So at this point, surprise, surprise, it's working much better than we thought. We don't have RAM, but Mike, who has made an FPGA AGC, has brought another board, and he jumps on the bed and starts coding. And he codes a RAM emulation memory board, which we wire in. So that was done in like a day. Right. We wired it in, and well, I was able to debug it because I had the logic analyzer, so we can figure out. So it didn't work first time, but eventually we get it debugged enough so that it kind of works.
And remember, all this development is happening in the hotel room, so it's not like a well-stocked lab here.
Right. So he's fearless. He says, "What are you going to run on it?" Well, I'm just going to put the Apollo 11 software and see how it goes. And it runs through 100 instructions. And at this point, we're absolutely elated. For it to go through that many instructions with our weird memory hack, a lot of things must be going right in that computer. So that's the happy hotel room restoration crew. We went much further than we thought. Unfortunately, we all have to leave. And so we all come back with a task. I get the module B12.
That's the RAM memory.
Right, that's broken. And Mike has read some reports that on the early memory modules, they had breaks close to the pins. And then if it's close to a pin, then we can drill next to it, and we can maybe fish it out and repair it. So we tried the X-ray. I work for Samtec connector company. We have very, very good inspection machines. Can't find a break near the... We know exactly which pin that is, right? So if it would have been obvious. Not in there, but it's a pretty picture. You can see how the core memory is folded in there and then potted. And then I have lots of test equipment. Those who follow the channel know that. So we try it with TDR. So we send a pulse in the wire that's broken, and we should see by the reflection how far the wires go. And it tells us it's smack into the middle of the module. So you can see where the two traces are starting to diverge. That's the difference between a good wire and a bad wire. Say, dang it, it's in the middle of the module. How are we going to repair that? And then you can also do it in the frequency domain. A wire of a certain length should be an antenna. You can measure the resonance. So I do it with a spectrum analyzer, and it tells us exactly the same thing. The wire is cut right in the middle of the module. Ouch. Not repairable. Oh, then comes...
So, of course, we have an Apollo guidance computer, but we don't have the interface to issue commands and see the responses. So there are a lot of replicas that you can buy, but they're designed to be self-contained. They don't have an interface that'll talk to a real AGC. So I put together a replica that was engineered to connect to it so we could use that to run the system. So here it is sort of being lit up and being driven by the AGC later on in the project.
So Carl it's more than a replica, it's a prop. You could put that in for a real AGC. You had the right color, the display is exactly the right thing, and the lines and all that stuff.
That is not electroluminescent, though. When you see a real electroluminescent display, it is so beautiful, the color. This is just
we were very impressed. We thought we had the real thing. And then a problem is how to wire it up. So it has these weird connectors. You can see them probably. It's the same ones here, right? It has the Malco pin connectors.
Mini-wasp.
Which Malco...
Mini-wasp.
Mini-wasps.
So this was something that they inherited from the Polaris, that they liked them on the Polaris, so they thought they'd reuse it on the AGC, and we wish they hadn't, because
nobody else on the planet used it, and they don't make them.
Yeah, so because it's a very dense connector, very modular, so it's individual little pins, and you can see actually the one that wasn't protected is in bad shape, and the right one was under a cover. That's the test connectors in good shape. Fortunately, I work for a connector company. And well, thank you, Samtech. They retooled the whole thing. I didn't have to push very much. Say, guys, can you save us? Can you retool the connector? Here are the drawings. We got the original NASA drawing, and the engineer was just flabbergasted to just redo it. And so we got our NASA pins. It was expensive. They had to do the progressive die tooling. That's we got great support here. The third thing we need is the test monitor. So the AGC is actually a blink and light machine. Just the front panel blink and light doesn't fly. So it has this big thing that is very powerful, actually. You can inspect every register, every location in memory, set breakpoints, and all that good stuff. Yeah, and Mike comes through again. He just reduced the whole thing in another FPGA board that plugs into the original test connector. And here is, actually, that's Mike with his simulated test thing. He has also an emulated disk key. And on the right, you have his FPGA test monitor, which is plugged on his FPGA AGC.
Layers upon layers.
Right. Finally, we convinced, so the problem is that the AGC is in Houston. The AGC is not separatable from Jimmy, and Jimmy is not separatable from his wife. But finally, we managed to fly the computer, Jimmy and his wife to California.
It's getting
Funny
expensive.
story about that. So we had it was Wall Street Journal, right, with the camera crew to watch the computer come in with Jimmy. So we're waiting at baggage claim because he checked it. And it did not show up. So here we have the baggage thing going around. We were in a panic. Luckily, it came a little late, but
yeah, they took videos of our decomposed faces.
that's when I decided it was going to fly next to me on every flight.
Right. So, but it shows up in the lab, and so now we are, as you know, if you follow videos, my lab is very well equipped. We can actually work on it. Our plan, and then the tester is there. We just plug it in there, and we have complete access to all the register. We know what's inside. So we have a computer, no RAM, no ROM. So the first thing is to make the ROM work, and this is Ken with his ROM emulator.
He pulled the bad straw, and he had
plug it in, and Ken, what happens?
Well, it didn't quite work. The main problem is they used these prototyping things that were called dipsticks, which clamp the dip ICs in between these two plastic things, and then one of the plastic pieces bows out, and you lose your contacts. So this was like popular for like about a week until they discovered these were terrible things. This box was not built to the same standards as the AGC. This was like, the low budget second string
Radio Shack thing. Yeah.
So, the components were terrible, the prototyping was terrible, the soldering was terrible.
You have to, I wouldn't say they were badly built, they were built by Raytheon, so there was by no stretch of the imagination a bad job, but it behaves like normal electronics. So it's more of a case that the stuff that flew on this AGC was incredibly well done, right? And that is more normal. So we have bad transistors, stuff, even the stuff that was welded disconnected. So we have to find where wires have to go. And then finally we fix it all. And it's still not working, and then we have to get the logic analyzer. That's not enough. Then we have to go in the scope and measure the current, and it turns out...
Yeah, the timing just didn't quite work, and we're not convinced it ever worked.
Right.
But adding a few capacitors, we lengthened the pulse. We lengthened it a bit too much. We changed the capacitors, got it to work. So we were finally able to get these core rope modules to provide data into the computer for about an hour. Then the plastic bent. It stopped working, and it's like, okay, enough of this. We're going to do Mike's approach with the FPGA. Yeah. We proved these boxes work. Now they're done.
Yeah, we got them to work, but so did we catch it in between revision? Because there were some wires that were missing too, right? It was one
Yeah.
transistor that went nowhere.
And there was some circuitry in there that just did not make sense. Like they had a parity circuit, but the computer already had parity and it didn't agree. And it's like, what are they doing? So it's kind of a mystery.
There was something like a transistor wired up backwards so it couldn't conduct, right?
Yeah, this transistor never would have worked. So was it a prototype?
But you finished the engineering. It worked afterwards. So we finished it. Right. So success, here is Mike on one side that is trying to read the core, the ROM from Ken, and some by miracles, some wizardry that I don't understand, they get it, right? So then we have to work on the RAM. So we had not tested any of the RAM circuit in the hotel room, so we start doing that in my lab, which is actually more complicated because it has core logic in it, which is another weird thing. And Mike right away discovers two faults, and he thinks those. So this is the thing that sends the current into the address wire of the core memory.
To read the memory or write it.
Right. For the addressing. And oops. And he thinks it's bad diodes. He's not too surprised because the diodes had been a failure in this module. This is the one big failure they discovered.
Mike is a walking Google search of anything to do with Apollo. He remembers every memo and every schematic and version. And he said, oh, there was a memo about this, and they disqualified the diode maker. And here's what would go wrong, and these look like it's those diodes.
Yeah, so he spent years, he read every single memo. It's extraordinary. So anyhow, we have to repair it, right? So what can we do? Well, we try all the chemicals we have at our disposal. There's nothing for that military potting. So module 11 gets in the mill, and then we mill it just on the type of the wires. And it turns out I have the pictures of the thing. So he said, I'm digging for the dinosaur, but I know where the bones are exactly, right? And so I know exactly which wire it is, and I can go in, and with dental tools, I can pick the stuff without causing damage. And eventually, we get there, and plus it's very strong, it's welded, right? So we opened it up, and nothing's broken. And it turns out we had reinvented, without knowing it, the correct method to rework those things. So later on, we would buy some more Apple hardware and would find modules with holes in it exactly like that. Mm-hmm. And it turned out it's a lady called Mary that was doing that with dental tools. So somehow we did it exactly the right way. We thought we had done a sacrilegious thing to it, but not. And we get to the diodes, they're bad, and then we just drill them out, right? It's core, it's cordwood. And then at lunch, we go to, those in the valley would know, Anchor Electronics. It's a 1N914. Do they have 9N914? Yes, they do. It's actually from the 60s. How much does it cost? It's 60 cents per diode. They haven't changed the price since the 60s. And so we put them in, and we see our module working. So we know the module works because of the purple trace. It must be able to give a current pulse in both directions. So that module works again. And so you see there's a couple pockets. There's already 4 pockets, 2 on the top, 2 on the bottom. So we are happy for an error until Mike calls me back, say, I found another problem. And this one is way worse. So this is core logic, which is another way. Maybe you can discuss it after. But it's a way to make gates with these little cores. You can do not only memory, but gates. And they are partly good at making short pulses, and which is great for memory drivers. So there's this little core with 4 windings around it, and he thinks there is something wrong and that they are shorted. The problem is that, and I dig another pocket, and sure enough, the location of the short is confirmed. And that's the component. It's very small, and it's potted itself. So it's a potting within a potting. And you can see the windings around it. But in the picture, there are 3, but in reality, there are hundreds of turns. So, and it's a very special core.
Yeah, they didn't have this at Anchor Electronics.
Right. Yes, it's something that's and so there no we're just crushed at that moment. And Mike actually turns out he has some of those cores because they're the same used in the core rope memory, and he starts winding stuff in the back of the lab, see if it would be possible, and on my own. So that's my lab book, and I doodle the one on the top. I say, okay, we have those 4 bobbins, and there's a short, that's the little thing that goes diagonally. And I've realized that one of the windings is to get the opposite signal to the second transistor. So one signal goes in phase to the first transistor at the top, the other one at the second transistor. And I go, oh, maybe if we make another transformer outside, we can invert the signal and recover that stuff and make it work again. And then Mike, we all look at it and say, well, that should work.
Yeah, we're trying to figure out this extra transformer. Mike says, well, why don't we just put in a PNP instead of an NPN to flip it the opposite direction? So
then blank. Would that not work? Would that? No, I think it would work. So you have the signal with the PNP transistor. So here comes the hack. You go snip, snip, and rewire a new transistor in there. Here's the new transistor. PNP. Right? And that should give us the opposite signal. And we test it again, and it's repaired. You can see the current going in both directions. Our PNP is a little too good, right? It's very fast, so we get these extra spikes, but that doesn't matter because the core has been read already, so that's fine. The hack works. We tuck it in, make it look like it was a factory. Then we are just one step away. We need to find a way around that bad bet. Fortunately, the AGC is a 16-bit machine, but it's really 15-bit plus parity. So Mike says, well, I can disable parity checking, and it's a wire wrap backplane, so you can carefully make modifications to the backplane, and we'll swap the parity bit for bit 6. We'll swap bit 16 and bit 15, and we'll just not worry about parity, and who cares what it becomes, we'll be fine. So that's what we do, and it's only 6 wires or something like that, with our memory ready to go back in. And then by that time, we have press, and we have the Wall Street Journal, and it's all exciting. And the question is, will it run? And I hope I have sound here. I do not. Well,
it'll show it here. Virtual disky, okay. Yeah. Okay, watch current.
174.
Hasn't changed. Okay, here it goes.
2.27.
That was
it's running.
Yeah, we got it display.
On its own memory?
Yeah, on its own memory. Okay, so...
actually, we had extracted the data reading one time, so we knew what had been in bit 15 before we did the swap.
So I don't know if you catch this with the sound, but that's the first time we run it, and it just ran. So we had done it perfectly right. So now we have a working AGC. What do we do with it? Well, the loop completes, right? The whole reason Mike was after making AGC work was to plug it in a simulation, so we do even better. Now we have the AGC hooked up to the simulation. We try to run it without the simulation, and it's kind of difficult because it needs the gyro, and it needs all the switches to be right. It needs to feel acceleration from the engine, or it shuts down with an error right away. So we got it working by putting no external inputs that were static, but then we modified any SSP. You can actually play it, all right? And we actually flew it and made landings with it. It was quite an achievement here to fly. And then we went on a tour to fly landings in front of the crowd.
We went to MIT and Grumman where they did the LEM,
and then we left. We were finished one day before we had to leave for the celebration of the July 1969 landing, with one day to spare. It always happened like this. So that landed us in the Daily Post of Palo Alto and Wall Street Journal too. Actually, we had the centerfold in there. Remember this guy, Alan Hall? And
Yes,
you
we flew
were
down.
there, right?
So first thing we did is we flew down to his retirement home with the AGC and ran the simulator and the landing so he could see again his brainchild doing the landing of an Apollo spacecraft.
And Mike flew landing in front of him. He gave us a few corals that he had under his bed, and we stuck them right into the computer and read them. And you know, I'll end it up here for questions. Thank you very much.
He had a question there. Right?
Yeah, I had a question earlier.
Yeah, sorry.
In the logic modules, are those ICs like still a standard package to this day?
No, it's like a resistor logic, no diodes. It's just
No.
Yeah.
I mean like the NOR gates.
yeah.
Or is the package still available?
Yeah, is like that package still a standard?
No, I think the flat packs are long obsolete.
Who else had a question? All right, hold on.
What was your success rate?
Hang on, there's a microphone going around.
Oh, excuse me.
But I can repeat the question too. That's fine.
With simulations for the LEM landings, what was your success rate?
No.
You mean hours or mics?
Anybody's.
I think Mike crashed once, and that was because of a software error. There was some problem with the simulated radar talking to the computer. Otherwise, he was perfect.
So Mike is very good at it, and in public he never crashed. But I tell you, I did it, and I thought it would be easy, right? The computer just navigates you and I crashed quite a few times before I could land it. So did Mike, by the way. And then the first time I actually landed, and this is in a simulation, right? My life is not in danger. The simulated engine's going to work. I don't have to report to Houston what's happening. My communication is perfect. When I landed the darn thing, my hair was like this on my, and I was sweating. And well, it was overwhelming first because that's the closest I would ever have been to the Apollo program. And also I realized what Neil Armstrong had said was so right. In Neil Armstrong's words, going around the moon, you know, that's a 7. Landing on the moon, that's an 11. And for me, it was a 20. It's really hard. It's really difficult. You don't put all the switches, don't follow the stuff, get a little bit of translational velocity. It's extremely unforgiving. So just to think that those guys, and mine was perfect. I have no 1202s, my communication is fine, my life is not in danger. I can't imagine that the guys, no, the communication is not working. Nothing's working, basically. You listen to Apollo 11 descent without knowing. You say, oh, this is cool. They go, we've landed. You listen knowing what's happening and what every call is terrifying.
Yeah, because when I say 1202, the screen went blank on the disk key, and he saw nothing. And then it would restart. And then at one point it got so bad, he said it was blank so long, I thought it was never going to come back. And so he said that all I was doing was making sure it was still responding. Because remember, that switch goes through the computer to turn the thrusters. So he said the moment it stopped responding, we were going to punch out of there. So it was like that close.
Yeah, so I really wonder what's happening, because that happened very, very low. His computer turns off, and when it's overwhelmed, it restarts, but it discards tasks that are not important, and lighting the disk is not important. So the guy is already, everything's gone wrong, he's not heading in the right position, he's going to the field of boulder, he takes it manually, but it's not manual. He's just telling the computer how to orient the thing. So he knows there is a computer between his stick and the LEM, and it's balancing the LEM. The minute the computer goes out, the LEM is not balanced, and it's not very high, right? There is one mode where you can fly it entirely by hand, and it was not considered flyable. And there's that button, and there's another button that says abort. And I wonder which finger he had. He must have been on one of those two buttons. I don't know which one it was.
Well,
but
one of the important things about the LEM is that we've been talking all about the Apollo guidance computer, and that's just a marvelous piece of kit. There was a second computer on the LEM. It was called the abort guidance system. One of the key things is if you had to abort and you had a working AGC, you never needed the abort computer. If things went to worms and you lost the AGC, that's when you just throw a switch, the other computer comes online, and you have all of your fly-by-wire and all the rest.
It was not very smart. All I could do was get you up into orbit, and then the CM would find you.
It'll get you home. It'll get you home alive. But we could spend a lot of time talking about the esoterics of it, and it was really more like, I don't know how many folk have programmed or worked on a Kim 1.
yeah,
It was about that level of sophistication.
right. Address,
Yeah.
memory address, whatever.
Yeah.
If you will.
When we get together for the Speaker's Corner after all this, we'll go over a little
So
bit on how you interface with this. Go
Right,
ahead.
but my thinking is that they had already broken the rules of abort 3 times, right? Communication not working, they give them a go, and you're not supposed to. Then they don't get high bit data rate, they get only low bit data rate. You're supposed to abort, they give them a go. 1202, that's a complete abort situation.
That was a wrong call by the people at MIT jumped up and said, no!
Long or wrong, but it happened to be.
The bigger story. The bigger
Right.
story is there's two different 12.0x alerts. One of them says that you're running out of your process slots. The other one said, and this is the amazing thing, this ran 5 what we call today, they didn't use the term then, virtual machines. 1962. And the 1202 alarm was that you were out of process slots for the virtual machines. Again, I exaggerate, it was called the interpreter. A couple months before Apollo 11, they ran a simulation and they injected those errors. And that's when they went, oh my God, what do we do? And the head of the computing group set up a cheat sheet that they kept on in the support rooms, and it said, if you got those alarms, it's okay, provided it doesn't happen a lot being undefined. And
Yeah, and provided you are not landing on the moon and at 1,000 feet altitude.
The biggest
right?
problem is
Simplified it.
There's this loop to like adjust the thing based on where you are, and if the code gets really behind, the thing's already pitched like this, and now you're firing the thruster the wrong way because of the big delay. So you would have gone unstable and maybe started spinning.
Well, I didn't finish what I wanted to say, but this 1202 is an interesting rat hole. But they had so third violation, they still land on 1202. That repeats 1201, so it's clearly written, don't do it if it repeats. I bet you, if it had gone any worse, Armstrong would have go manual. He would have landed somehow. He would have not punched.
once you get low and slow,
we have already rejected the abort rule 3 times. I am at 300 feet. I'm going to try.
I don't know how many pilots there are. I was a pilot for years. One of the things is when you get low and slow, your only option after a bit, if you can't go around on a bad landing, well, you're kind of committed to putting those wheels on the ground. Somewhere, one way or the other, and hopefully in one piece. Once you got down, and again, I've read various numbers, once you get down to a certain altitude, they call it a dead man zone. You don't have enough time to fire the abort engine and get the heck out of there, the ascent engine. So once you get to a certain point, you're committed one way or the other. You're going to be on the surface, hopefully in one piece.
Are there any other questions from the audience?
Yeah, I was thinking with all these emulators and so forth. So these are all of this stuff was built with the 0.5 volt TTL levels, I assume, right?
0 to 4 volts.
Yeah, and it was not
DTL level.
yeah, not
So it's not
Not TTL,
TTL. TTL is far into the future.
This is
here.
resistor transistor.
I was joking.
Okay.
I was wondering just how bad it was.
So the question was how bad the
What kind of voltages were they?
0 to actually 0 to 4 volt is the
Logic.
power to the logic, but what was the 0? What was the
I think
one?
it's close to 3.6. I worked with some RTL stuff back
Right. So I don't, and it is circuit number 1. That's something that Mike would know. He
It's
would
sort
have
of like
to save us.
how many combiner it fans out to changes the voltage a bit with the RTL.
So I don't know, but it certainly didn't have the noise margin of TTL, if that's the question you're asking.
But one curious thing you might have noticed from the modules is there are no decoupling capacitors at all. They discovered it worked better without them, and with this logic family, that was okay.
Yeah, and but the other thing is that this thing was incredibly reliable. It never failed. And then I learned recently doing the F8 video, because they reused that computer for the F8 fly-by-wire on an actual airplane later on, which is more difficult than a space thing, because you have all kind of known idealities when you fly through air. And the AGC was used in the first part of the program, interim, because it was there, and then they were going to use the IBM AP101, the same that in the shuttle. AGC didn't fail. The IBM AP101 mean time to failure at the beginning of the program was 300 hours. And they got it up to 500 hours by the shuttle time. It's just how incredible.
That's why they had 4 computers.
Right. Yeah, they beat it by, and that's IBM just poo-pooing that computer. Oh, they don't know how to build it reliably. And it was incredibly reliable despite its very controversial choice of very new technology.
Yeah. You have to remember at the time when that decision was made, and we'll say that was roughly 1961-ish, mean time to failure for logic gates, if you want to even call them then, was hovering around 12 to 24 hours. And you hear about, pilots didn't want a computer, and well, geez, by the time you got your wheels up and you're off the ground, the damn thing has died. And so, yeah, that was a gutsy move.
Yeah, so I think the decision is a little bit later. I would have to look. So there's the memo that Eldon Hall did. It's really a Eldon Hall decision. And he saw the writing on the wall. We are not going to hit the target weight and space if we don't switch to something more integrated than what we have. So it already had gone through convulsions, the how do you call them, the core logic implementation, then the transistor implementation. And then during that time, Eldon Hall places an order of ICs with Fairchild, Fort Philco, I think. What was the third one?
Texas Instruments.
Texas Instruments. And then nobody delivers but Fairchild. And Fairchild, people that will go on to make Intel, they already show their mastery at producing, delivering stuff. So I think he got one maybe from Texas Instrument. Fairchild delivers 35. He goes, tests the first 35. They test good. And he writes a memo, I don't have time to do reliability, but I don't see why this would be any less reliable than transistors. Therefore, we need to change for ICs. Eldon Hall, go for it, right? Of course, he would never made it at IBM, but it was actually the right decision. And it was a very gutsy one, but with the good guts, right? He was totally right.
Yeah, yeah. Am I correct? I believe I remember Eldon saying, Eldon Hall again, the chief engineer, that the flight modules ended up being all from Philco?
Mike would have known which one.
I don't know. I thought they were made at Raytheon. I mean, the ICs.
Yeah.
Yes.
Oh, this I don't know.
Okay.
I just know the decision was based on Fairchild.
We know that
I think you're
colored
correct.
dot.
I think you're correct that they might not, in the end, the one they qualified, which was, of course, several years later, might be from a
They actually
different
flew out to Silicon Valley and inspected the manufacturing and taught the manufacturing industry how to get rid of the problems they were finding in the chips. So they greatly improved the quality of integrated circuits.
Yeah, this is one of the important things. Of course, NASA didn't invent the microchip or anything like that, but they put out these absurd requirements that for industry to meet, and they said, here's some money to make it work, and that is the real benefit for the semiconductor industry of Apollo. They forced the manufacturers to learn how to do it really well. Any others? Because I don't want to run out of time, or want to leave with you have some questions.
This mic is okay. Yeah, I believe that the RTL chips, they were Fairchild 900 series, and they're 3.6 volt or 4 volt logic. I have some equipment that's still running using those chips. And my Uncle Frank, he was a technician. He worked at Bendix on components of the LEM. And he said his initials are scribbled on some equipment that may still be, on the moon, part of the platform. Yeah, my late Uncle Frank. Gentlemen, it's really curious, Mark. I love following your videos, and a great job. A labor of love in that project. Appreciate it.
Thank you very much. There's a question over there in the corner. Nobody sees the question, so I'd like to, if we could get the microphone over there.
We're making the poor guy run.
Yeah, we're trying to get some balance throughout the room. That's it.
Sorry to jump the line. Given how advanced this was, do we know how the Soviet moon program, if they would have solved it in a similar way? Do we know anything about that?
All from the ground, right?
Yeah.
You want to answer that? I have some answers, but... okay. The Soviets, to call their systems computers is a bit of a stretch. No, I'm not beating up on Russia. I mean, this is... technically, yes, it's a digital machine, but they were more like sequencers. Not a fully programmable, like traditional way we think of computing today. The LK lander had some, I want to call it automation, mostly because that was a design philosophy of the Soviets back in the day and the Russians today. You really take a lot of the decision-making out of the hands of the pilot. Apollo was 180 degrees out of phase with that. They insisted on having their fingers on everything. Russia, I'm not going to be crabby or whatever. I don't want to say that they were just there for the ride, but they had far less interaction between the astronaut and the spacecraft and whatever mission.
Yeah, but they didn't have near the capability of electronics.
No,
so I don't think there was any guidance in the ship that was planned. So it was all guided from Earth, which, by the way, on Apollo, if they had the IBM 360 on the ground telling them that's the solution, that's the one they would follow first, right?
Yeah. Even though the AGC was perfectly tracking where they were, they kept sending up updates from radar and from the ground, saying, update your state vector, here's where you are.
Yeah.
Because they trusted that more than they trusted the computer.
And that was a mission rule that they said even before any of the missions was that, okay, if given 3 options, we're going to go with the ground solution. It wasn't like, oh, we don't trust it. It was like this was a rule written before the flights.
Yeah, refs mad up.
Well, but when it came to guided landing on both the moon and Earth, that was AGC without no help.
Yeah, time lag. You couldn't do it from the ground.
Yeah. Right. So that's something that the Russians could not do, and that's why they landed so far from their targets.
Yeah. Again, there's few things that can replace a perfectly good Mark I eyeball. And no, deadly serious. I mean, again, yeah, we can talk about auto land on airliners, but honestly, having someone there with a skilled pilot with a good set of eyes and workable controls, that is really a perfect man-machine kind of synergy.
Is there a question here?
You guys mentioned early on that there was 3 DSKY consoles. Was it 2 on the LEM and 1 on? There were
2 on the command module, 1 on the LEM.
How were the two on the command module wired to the?
So they actually had like two sets of connections into the disk key, one for the primary, one for the secondary. Although you could use either one, but they just happened to be wires for two. Because if you were down in the lower bay looking through the telescope, what they did was they found stars to verify that their position was accurate. So they'd like click a button pointing at stars, and the computer would update its notion of where they were. So that was done from down below the seats, and then the disk key was on the control panel when they were flying in the seats.
But to simplify it greatly, they were basically in parallel with each other.
I know you guys have been collecting mission core ropes, or at least the contents of the core ropes.
Yep.
How many missions have you collected so far?
Let me go. I have some. These are the extra slides. Actually, why I have them. This is the LTA8. It's still there. Still in Houston. It's
You
the
can look
one
on the back wall and see it's missing. An AGC.
I have. So that's where our AGC came from, and that's LTA8 in the vacuum chamber with the astronauts getting in there. And if you squint and look at the back wall, the door is conveniently open. There is no AGC there because we had it. Okay, let's see. The question was...
How many missions? I'm sure Mike's updated it since whatever you have here.
I have... there we go. So this is old now, but this is what we have recovered so far.
Yeah.
So not just mission software, but also test software.
Yeah. Now, there is a website that a gentleman by the name of Ron Berkey manages where you can get the listings for most, not all, of the Apollo missions. And it's amazing to watch that evolution, to see how...
This is what Mike keeps updating.
Yeah.
Yes, that's his source.
Yeah.
So not only does he dump the software, but then he decompiles it and try to understand what it was supposed to do.
What was the change? He figures out why they changed this and that from one.
So it's a good example is the AS202, which is in Oakland, and nearby I made a video on it, and then he recently got, so that's block one thing, and then he discovered, before I found that paper, that he flew, so gets the software, flies it. So AS202 is one of the first missions descended up in suborbital, and this first time they tried a computer, so they tried to have it orient the spacecraft and do some burns. And he runs it, and he finds that he has like this weird 3-second burns before it re-enters. And I found that document, and yeah, you see the little weird 3-second burns in there. So we recovered the right software. So there's just way more than just recovering the software that Mike does. He's amazing.
So if you know anyone who happens to have ropes lying around, tell Mike.
He doesn't need to keep them. He just wants to read them and give them back.
When you search for Apollo ROMs on Google, it's gotta be in China somewhere.
Computer
It'd be in eBay.
Yeah.
The last one he recovered was Skylab, I think. He has some Skylab ropes.
Yeah.
The energy supply on both the command module and the LEM was obviously quite limited, and particularly so on Apollo 13. What was the power consumption of the AGC?
50 watts, wasn't it?
50 watts.
Yeah, 50, 55.
And so it used switching power supplies for efficiency. So back then switching power supplies were pretty uncommon. So they got much more efficiency than they would otherwise.
Yeah, so 50 watts fed by 28 volts from a spacecraft, bus A or bus B.
Again, please.
Of a light bulb, yeah.
Yeah, the AGC is it's just the computer, but it's the whole system, right? The more power-hungry things were the gyroscope, the PSA, the CDU. So there's way more that makes the system, and it's fairly power-hungry by the time you're done. But they had so much power inside that spacecraft because they had 3 times 1.6 kilowatts if they wanted to, except on Apollo 13 where they had
Zero.
But they had lots of power thanks to the
Fuel cells.
The fuel cells.
But on the LEM, it was batteries. They didn't have fuel cells there, so
That is true.
They're considerably more limited.
Yeah.
But shorter mission.
And for the, well, it's a much shorter mission, but for the later Apollo missions, they actually powered down the computer just to save on power. You had 5 400 amp hour batteries.
Oh, really?
And that's not a lot. That's not a lot. But
question over there.
So earlier you mentioned that you hooked up the diski and hardware to a flight simulator and ran the landing yourself. Is that simulator publicly available, and can we try?
You can, in fact, download it and use that the emulator that Mike got to work perfectly and fly the missions yourself.
Yeah, it's been around for years.
Yep.
What's the name of the software? Where can I find it?
Mike,
Orbiter.
I mean, Mark, you know, right?
It's called Orbiter with the, so search for NASSP. It's rather difficult to install. I need to make a video on it because it's all, you have to put the package from there, put the package from here, and only the Mike and a few others can do. But they have flown the entire mission on the thing. It's
and they've saved the state so you can like get it where you're in orbit of the moon, Apollo 11, just before you start landing. Start up that thing and just go through the checklist and land.
It's a crazy package because some of the stuff is written, it's a true almost crowdsourced where everyone's writing in their own favorite language. There's modules that are written in, I'd never heard of it until then, Tickle?
Yeah, oh yeah, sure. Tickle on
I mean,
you're space guy, not the computer guy.
So Tickle was written by my advisor in grad school, by the way, John Osterhout.
Oh, so I don't know if you want.
That's right. Yeah, he likes
Tickle TK.
Oh, okay, that's fine.
I wanted to ask about the clock speed and how was that defined? What was the maximum, and was it overclockable? Or
So you're happy to have a clock.
So they started with a 2.048 kilohertz or megahertz clock, which they then divided by 2 immediately. So the processor was basically 1 megahertz. Each memory cycle took 12 states. You might remember from that the logic analyzer at the beginning, we saw it go through the 12 states because with core memory, there's a complex process to get the data and then restore it. So there were 12 milliseconds there, and then you had to do one of those large cycles to get the instruction, and then another cycle to execute the instruction for the best case. So it was...
Could have been 24.
Yeah, so basically a 24 microsecond instruction for your simple instructions. Multiplication, division took longer.
And then for complex math, they had this interpreter, which had this very rich instruction set, but very slow because of the virtual machine.
And this is what I, kind of jokingly, but not completely inaccurately refer to as the virtual machines. It's the interpreter is comparable to like a Java bytecode engine.
So the interpreter, for instance, you could do sine, cosine, vector operations, matrix operations as your machine instructions, and then it would be interpreted. So it saved a lot of programming effort. It saved a lot of memory, but it was an order of magnitude slower. So for navigation, where speed wasn't very important, they would use the interpreter. For engine control, where you had to respond immediately, that was written in the low-level machine language.
Right, and there was no floating point. Right? Floating point was also in the virtual machine, correct?
Yes.
Mm-hmm. Well, the brilliant thing is, and this predates the Apollo guidance computer, is actually something IBM had in the middle 50s, was you used what was called a fractional notation, and it was implemented not unlike a slide rule. You could do, quote, quote, floating point with regular integer math, but the thing is, you'd lost your exponents. But if any of you used a slide rule, we're all comfortable with managing our own exponents ourselves. And so they could do all the math, just as long as in the back of your mind you know that this is going to be an order of magnitude of this.
There was a good one by Dan Lickley when we interviewed him. So it's all fixed point, right? So they scale the problem when they need to. So he said, well, if we don't hit the moon,
we are either going to be halfway there or 2 times too far. But all in all, it's a very slow machine, and that's why it took 2 seconds to complete a guidance cycle, which fortunately in space is fine. And you can actually see it in the footage, particularly in the footage where they take off.
Yes.
You can
Very
see
clear.
the thing go beep, 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 every 2 seconds.
It looks like it's nodding.
Yeah. But it turns out, and it's a very simple calculation, right? It's perfect gravity stuff, right? But it's very slow computer.
But flying at F8 with something with 2-second response time was...
Well, that was an inherently stable plane to begin with. So but just a heads up, we have about 5 minutes, so let's start ripping through some of the more questions. And
we got one.
So the orbital mechanics has not changed in the past 50 years. The kind of speeds you do things in space are very similar. Could you run a modern spacecraft with this thing? Like, a lot of the math you're doing is the same. Like, Kalman filters are still the way we do a lot of this stuff. Is there anything fundamentally different now about spacecraft that they're doing that, like, you need so much more computer?
You do a demo scene version of that. Of a spacecraft. I think that's pretty interesting.
If you look at the reaction time you need to be able to have a rocket booster come down, come to a stop stably and not fall over on a barge that's tipping, that's a lot more computer power.
Yeah.
They actually do max out their computer power on the SpaceX re-entry.
Yeah.
And the guy says, "Oh man, if I could only have a more powerful computer, I could do so much a better job." But it did completely max it out.
Now,
but I mean, nobody thinks about it because it's just so simple. I mean, you do that because you're forced to. There's just no other solution, right? And it's a feat of doing it, but. It's a rather simple calculation, and things happen fairly slowly, so you could actually do it.
There were also a lot of bodies involved in Apollo, right? So you have all these people in back rooms and calculating things, computers in the Johnson Space Center calculating things, sending commands up. So it wasn't just a computer; it was this whole support group of people all over landing it. Whereas today we sort of think about send one up and the computers on that spacecraft can take care of all of it without needing these thousands of people supporting it.
Yeah, but still, one of the Apollo 8 thing is that they proved that if they actually wanted, they could have flown all the way back with just the AGC, with a lot of effort.
Yeah, there have been skepticism, but just by star tracking to update the accuracy, they would have been able to do it perfectly.
The ground solutions, and again, the AGC solutions were really spot on to the point where if they had lost communication, remember, Apollo had to act autonomously if necessary, if the Russians were jamming, which was a real thing, real worry. They would have been able to complete the mission as advertised.
Yep.
You know, and it's really pretty much just flying the standard flight plan that they were going to if they lost communication.
There's so many belts and suspenders in the Apollo program.
Completely.
Yes. Were you able to recover despite the core memory contents, despite the fixes you had to make, and the fact that you had to retry several times in order to...
We very carefully checked everything to make sure it was going to be right, and we had one try and one try only. Before we rewired the bits, Mike read it all.
Right. So we could read it. It would just destroy the content. So once we got all the circuits, we did one pass where we dumped it, and then we modified the.
And Mike looked at it, and he knew what had been running, and it had gotten a shutdown kind of command entered, and it had the geographic coordinates of the Johnson Space Center in memory.
Yeah, so we know exactly how it was, what program it was running, and where it was.
That's beautiful. Do you know if any other AGC memory contents has been recovered and
We don't
be
RAM,
interesting in it?
Don't think so.
Yeah, I think ours is the only one that's been powered up in decades.
If you have another one, we'd
I'd be happy to.
love to.
I mean, the data's probably still sitting in the core memory of all the other ones, but nobody's looked.
Yeah, core memory is incredibly stable.
Yeah.
Yep.
There's
Anything
another
else?
computer not been discussed by you guys, obviously. The instrumentation unit in the launch vehicle.
Right.
Correct.
Has any efforts made to make anything out of that?
Yeah, we've looked at the LVDC, and we were asked if we could read the data out of the core memory of that one. The problem is a bunch of the chips were physically broken, and so we're like, that's not going to work. There was also, in the Saturn V instrumentation unit, there was an analog computer, this big, heavy, round cylinder called the flight control computer, and we've considered powering that up and running it. But honestly, what it does is not too interesting. It's basically just doing some filtering and for the engine controls. But yeah, it's on our list, I'd say.
We should do
Yeah,
it.
wait, in fact, just last night we were talking about
it's,
IU and yeah.
It's still.
No, I think the AGS, the abort guidance system, is the one I'd be most interested in seeing, because there's like almost nothing
on it.
nothing about it.
But the IBM is quite interesting because it didn't fail either. Completely different approach, triple redundant, very conservative design, and it worked fine. Man, it was zapped pretty bad on Apollo 12
with the lightning strike.
Yeah, discarded.
Although if you think about
the bad data kept going. So
but the lightning hit the command module and then went all the way down to the IU. So
yeah, so it did very well. It's an interesting computer. Don't know how much I want. I can say at least that we have Mike, of course, has a running model of the LVDC at this point.
Yes.
Yeah.
Holy smoly.
And it gets you to orbit.
Well, his day job is he does navigation software for a company that does infrared surveillance satellites, Capella Space. So that's his day job, is supporting those and supporting launch.
But on the Apollo program, he's doing the core rope recovery disassembly. He's doing LVDC, and he's doing the CDU to get to the bottom of the 1202, 1201, which is another story.
You wouldn't believe how deep in the rat hole we've gone on that.
And then plus we work on the Apollo communication system.
Yeah.
So we're not done with this whole thing.
The CDUs are effectively A to D converters that take data from the inertial platform, which is inherently an analog system, and also the radars and the sextants. They convert it into a format readable by the AGC, back to digital, and they're beasts. They really are. If you look at the diagram, and again, we're running out of time. If you look at the diagram inside the command module, those take up as much room almost as the computer itself.
Yeah,
and there's 5 of them.
Box the same size, was covered with modules, very complicated.
See, if they only just waited for the computer to read it, we wouldn't have had a 1202 alarm. But what they do is every time they're coming up with a different answer, they interrupt the CPU to update a counter. And so it was all of those interrupts is what drained the capacity.
So there's a CDU, right? So actually, that's the complete system.
Yeah.
You have the gyro on the
that globe thing.
Inertial platform, AMU. The AGC, you don't see it, it's behind the gray box, and the CDU is on top. Same size as the AGC, and very complicated thing. We now have, Mike has 3 of them.
I don't know, but Mike.
Including the one with the holes in the module.
Did the guidance computers on the landing module and the command module talk to each other, or were they fully independent?
No, they were very independent.
But the guidance computer in the command module could steer the Saturn V. So it got all the data from the Saturn V and was monitoring it and could take over.
Yeah. One of the crazy things is that, yes, there was a switch on the panel that said Do you want to use the inertial, the instrument unit on the Saturn V or the command module computer? And if that went to worms, you could, and Dave Scott, one of the commander of Apollo 15, told me this was doable. You could hand fly the Saturn V to orbit. And not very well, but you get into a stable orbit. It's a little bit dicey, but yeah. Now think of how metal that is. Sitting there driving a Saturn V with a hand controller.
You just look for where the moon is and make sure you're headed in that direction.
Kneel a little bit to the right, please. Right. It's still the okay, go ahead. Questions.
Yes. What's coming next for the Apollo program? I know you've done the communications. Been watching that with great interest.
I'm trying to move on to the shuttle.
Well, I thought you were going to be building a complete Apollo spacecraft, though. It seemed like it.
We are inflating the Saturn V as we speak in my garden, but
and it digs so that the local planning people wouldn't see it. So it's
yeah.
We keep receiving so much. It is just where we go from there. We are probably going. I want to take a breather actually to get to the IBM stuff. But there's the CDU story going on. There's the LVDC story going on. Plenty of stuff still left for us to do. There's quite a bit of hardware that we have access to now. It keeps coming. Wow, we have exhausted all the questions on time. Incredible.
So it's... It's 3:30. Normally, no. If it's 3:30, we would normally say, "Hey, we have the next person coming. We all have to go." This happens to be the last talk of the last day, and so if you want to hang out and ask questions, and if you want to sit and answer questions, we're good to go. You know, it's really all about you. You have. You know,
we're like
I can
if
show
you
my
keep asking questions,
extra
we'll
40
be here all
view
night.
graphs.
So if you want to hang out,
I do have 40 extra view
if
graphs.
you want to, but we have time and you can keep going.
And we got the beer.
Any questions?
No?
More questions?
Okay.
Yeah, we're here all night.